Hello students, welcome to the fourth session of our first module. And in this session, we are going to discuss about some of the problems related to the concepts or cycles, air refresh cycles we have already learned, like Coleman cycle, Carnot cycle, and all. So I will do a couple of problems. So before that, I have asked you to write an assignment to find the equation for COP. COP in case of Bell-Coleman cycle. Bell-Coleman cycle with polytropic expansion and compression. Polytropic expansion and compression. Right? Have you done it? So I hope you have done it, but I will explain it as those who have understand those things. So our Bell-Coleman cycle is like this: 1 to 2 uh, 1 to 2 compression, adiabatic compression means PV raised to gamma equal to constant. 2 to 3 in PV cycle, constant pressure, heat rejection. 3 to 4, what was it? PV raised to gamma constant, isothermal, sorry, adiabatic expansion. 4 to 1, constant pressure, P constant, constant pressure, heat addition or refrigeration. So here Q equal to 0, here also Q equal to 0. Here refrigeration Q add, Q addition, here Q rejection, right? So two process in constant pressure process, Q rejection, Q addition takes place. Other two, compression and expansion, are purely reversible adiabatic, means isentropic process. So students, in case of polytropic process, 1 to 2, 2 to 3, 3 to 4, 4 to 1. So students, you have to note that this process is based on PV raised to n equal to constant, a polytropic process with n as a polytropic index. So this is also PV raised to n equal to constant. So here P constant, no change. Here also P constant. So the important thing you have to note that here Q addition take place, Q addition, here Q outside, Q rejection, but here Q not equal to 0. Since this is not adiabatic, purely adiabatic, so there might be some heat transfer. Here also there might be some heat transfer, either in either direction. So you don't know about that. So it is, since those two compression and expansion processes are not adiabatic, you cannot write the, while you are deriving COP equal to desired effect Q addition by network, right? We write like this, right? So while finding work, actually in the previous case, we have written it like Q rejection minus Q addition, right? Q rejection minus Q addition. Okay. So this is not applicable in this case, because there is a heat transfer in both all the four processes. So two more terms will come. Two more Q1 Q1 to 2 will also come, plus Q uh, 3 to 4 will also come. So it will become a more complex. So instead of writing W in terms of Q, net work transfer in terms of net heat transfer, you can write Q for, sorry, work net can be calculated from uh, work in case of compression minus work in case of expansion, right? So in case of compression, since it is a polytropic process, from 1 to 2, from 1 to 2, or 1 to 2, okay, 1 to 2, you can write n by polytropic index is n. You have already studied to write the equation for work in case of a polytropic compression in your thermodynamics class. So if you don't remember, please go back and check those things that you have studied. Okay, it is P2 V2 minus P2 V2, P2 small v2 minus P1 small v1, or you can write it as n by n minus 1 into R T2 minus T1. Okay, so take it as, keep it as equation number 1. Similarly, work expander is nothing but 3 to 4. It can be written as n by n minus 1 into P3 V3 minus P4 V4. Okay, that is equal to n by n minus 1 into R T3 minus T4. Keep it as equation number 2. Okay, so using 1 and 2, you can write network as n by n minus 1 into R, right, R into T2 minus T1 minus T3 minus T4. So this is how you write network. So Q addition is nothing but Cp T4 minus T1. Okay, so you can get COP as Cp T4 minus T1 minus T4, not T4 minus T1. T1 is higher. T1 minus T4 by n by n minus 1 into R, keep T2 minus T1 minus T3 minus T4, right? So since R is nothing but Cp minus Cv, if you take Cp common, Cv, take Cv common, we will give Cp by Cv minus 1, right? What is Cp by Cv? Cp by Cv is nothing but Cv into gamma minus 1. Okay, so you will get R equal to Cv into gamma minus 1. So substitute for this R. So it will become COP equal to Cp T1 minus T4 n by n minus 1 into Cv gamma minus 1 T2 minus T1 minus T3 minus T4, right? So you take this Cp to denominator, it will become Cv by Cp. What is Cv by Cp? 1 by gamma. Cp by Cv is gamma, this will become 1 by gamma. So equation will become COP equal to T1 minus T4 by n minus 1 into gamma minus 1 by gamma into T2 minus T1 minus T3 minus T4. So this is the equation case of polytropic process, polytropic expansion. So if n equal to gamma means the polytropic process is nothing but adiabatic process itself. So in that case, these two terms will get cancelled because n by n minus 1 will be equal to gamma minus 1 by gamma if n equal to gamma. So the remaining equation, the equation we are left with will be the same Same equation that we have already got while we were deriving the COP in the previous case. Okay, so there we can use the adiabatic equations and solve this and solve this equation to get COP equal to 1 by 1 by what was the equation? Rp raised to gamma minus 1 by gamma minus 1, right? That equation again. So COP in case of polytropic will be equal to T1 minus T4 by n by n minus 1 into gamma by gamma, sorry, gamma minus 1 by gamma into T2 minus T1 minus T3 minus T4. Okay, now we can do some problems. So are you ready? Okay. So students, please note down this problem. A cold storage is to be maintained at minus 5 degrees Celsius. Okay, so 268 Kelvin. So the sink temperature, the temperature of the space to be cooled is 268 Kelvin, while the surroundings are at 35 degrees Celsius. Means source temperature, the higher temperature or the ambient temperature is 35 degrees Celsius. The heat leakage from surroundings into the cold storage is estimated to be 29 kilowatts. So the surroundings heat is getting leaked into cold storage. So the rate of heat at which the leakage is taking place is 29 kilowatts. The actual COP of the refrigeration plant is one third of an ideal plant working between the same temperatures. So find the power required to drive the plant. So students, please note down this problem. Okay. So what was the problem? I have a refrigerator, right? A space to be cooled with T1 equal to minus 5 degrees Celsius. Some Q1, some Q2. This outside temperature is, what was the temperature? 35 degrees Celsius, right? 35 degrees Celsius, T2, right? So we have to apply some work. Some work should be provided. So it is given that actual COP is equal to 1 by third of ideal COP. So students, what do you mean by ideal COP? Ideal COP of a refrigerator is nothing but the COP of that particular refrigerator working between the same source temperature and sink temperature but operating in Carnot cycle. So Carnot cycle is the ideal cycle. Carnot cycle. When working between the same temperature and the cycle is undergoing a Carnot cycle, then the COP will be ideal COP. So students, we have COP, we don't have the value of COP, but it is given that from surrounding 29 kilowatt of heat is being leaked into the space to be cooled. So in order to maintain the temperature of the space at minus 5 degrees Celsius itself, what we have to do, since 29 kilowatt is being leaked into this particular space, in order to maintain this temperature at the same level, what we have to do, we have to pump 29 kilowatts, we have to we have to extract 29 kilowatts from that same space. So Q1 will be 29 kilowatts. So whenever 29 kilowatt of heat is getting leaked into the system, we have to extract 29 kilowatt using a refrigerator. So Q1 will be 29 kilowatt. So students, COP is nothing but Q extracted or Q extracted by Q reject by W. So or Q1 by Q2 minus Q1, or Q1 by W. W is nothing but Q2 minus Q1. But for ideal cycle, that is Carnot cycle, Carnot, we have derived COP as what? Lower temperature by higher temperature minus lower temperature. So what was the higher T1? T1 is lower temperature, means 2. So T1 is minus 5 degrees Celsius. It means 268 Kelvin. T2 is 35 degrees Celsius. It means 308 Kelvin, right? So therefore COP is equal to 268 by 308 minus 268. So if you calculate this value, you will get around some 6.7 COP. So this is ideal COP. But actual COP is 1 by third of ideal, right? So 1 by third of 6.7 will be some value around 2.23, right? Some 2.23. Okay. So COP is equal to Q1 by W, right? So 2.23 will be equal to Q1 is 29 kilowatt and W is unknown. So we have to calculate W, the power required to drive the refrigerator. So W will be what? 29 by 2.233. So kilowatts. So it will be some 12.98 kilowatts. So this is the amount of power we have to add to the provide to the refrigerator, so that we can maintain the temperature of the cooling space at minus 5 degrees Celsius itself. So this is a problem related to Carnot cycle. How in the problem it was nowhere, the name called Carnot was nowhere specified, but you have to understand that this problem is based on Carnot cycle, because in that problem a word called ideal COP is specified. So ideal COP specified means you are supposed to use the equation for COP in case of Carnot cycle. So otherwise, some another word called minimum work. Sometimes this cycle is operating with the minimum work. Such expression will be given. So in such expression, a minimum work means a maximum COP. Maximum COP is in the case of Carnot cycle. So if such words are used, you have to apply the equation for Carnot cycle. Okay. Hope you have understood this problem, and we will move to the next problem dealing with Bell-Coleman cycle. Okay, Bell-Coleman cycle. So students, this is a problem based on Bell-Coleman cycle. It is directly given. A refrigeration machine of 6 tons. 6 tons is the capacity. Working on Bell-Coleman cycle, and has an upper limit pressure of 5.2 bar. The maximum pressure is 5.2 bar. The pressure and temperature at the start of compression are 1 bar and 18 degrees Celsius respectively. The cold compressor enters the expander at 41 degrees Celsius. Assuming both expansion and compression to be adiabatic with an index of 1.4, calculate COP, quantity of air circulated per minute, piston displacement of compressor and expander, bore of compression expansion cylinder when the unit runs at 240 rpm and is double acting with stroke length 200 mm, power required to drive the unit. So students, the total capacity of the refrigerator is 6 tons. Upper limit pressure is 5.2 bar, means maximum pressure after compression. It is P2 equal to 5.2 bar. Pressure and temperature start of compression are 1 bar and 18 degrees Celsius, means P1 equal to 1 bar, T1 equal to 18 degrees Celsius. The cooled compressed air enters at the expander at 41 degrees Celsius means T3 41 degrees Celsius and gamma equal to 1.4. Okay. So students, this is a Bell-Coleman cycle. In the given question, we have certain values already given in the equations are given, or it is given that P2 maximum temperature. So this is the maximum temperature limit. So P2 equal to P3 equal to how much? 5.2 bar. Okay, 5.2 bar, right? And another thing given is P1 at initial before compression, starting of compression, pressure equal to P1 is given. P1 equal to some 1 bar. So P1 will be same as P4, right? And also T1 is also given. It is 18 degrees Celsius. 18 degrees Celsius, right? So 18 degrees Celsius. Now 18 will be equal to 273 plus 80, 283, 291. 291 Kelvin. But T1 will not be equal to T4, right? Only P1 and P4 will be equal, but T1 won't be equal to T4. Okay, so just don't confuse with it. So another point is given T3, the temperature at the entry of expander. T3 is equal to some 41 degrees Celsius. So T3 is 41 degrees Celsius means 273 plus 43. How much? 41? 340, right? 314 Kelvin. And also gamma is given. Gamma 1.4. So what we have to find? First we have to find COP. COP. How to find COP? COP is given by Q by W. Q refrigeration effect or refrigerated amount of heat by W. How to find Q? Q refrigeration is nothing but Cp in that process of 1 to 4 to 1, right? T1 minus T4. Okay. And W is nothing but Cp T2 minus T3 minus Cp what T2 minus T3 minus T1 minus T4. T1 minus T4. Now we have the values for actually the values of T1 is given, T3 is given, but T4 is unknown, T2 is unknown. All these values are unknown. So how to calculate those values? How? So those values can be calculated uh, using what? P3 by P4 equal to T3 by T sorry T3 by T4 equal to P3 by P4. The equations for gamma and the what adiabatic equations. But we have already derived an equation for COP in case of Bell-Coleman cycle. What was that equation? What was that equation? 1 by Rp raised to gamma minus 1 by gamma minus 1. This was the equation. What was Rp? Rp is nothing but pressure ratio P2 by P1 equal to P3 by P4. So students, we have these values already with us. What is P2? 5.2 by P1 will be 1, right? So if you substitute for this equation 1 by 5.2 by 1 means 5.2 into 1 minus 4 minus 1 by 1 gamma minus 1 by gamma minus 1, you will get some 1.67 as the value COP. So if you have the value of COP, you can calculate you can calculate COP equal to Q by W, right? So you have the value 1.67 equal to Q by W, but you don't have the value of either Q or W. That is why we have written the equation Q equal to Cp T4 minus T1 minus T4 and W equal to Cp T3 minus T2, sorry, T2 minus T3, higher minus lower, okay, T2 minus T3 minus Cp T1 minus T4. So here we have the value of T1 and T3, T4 unknown, T2 unknown, okay. So to find all those things, we are using the equation what P2 by P1 equal to T2 by T1 into gamma minus 1 by gamma, okay. Since T1 is known, P2 is known, P1 is known, gamma is known, all this, you will get T2 equal to some 466 Kelvin. Just check it, okay. Similarly, P3 by P4 raised to gamma minus 1 by gamma will be some T3 by T4, and you have the value of T3. You have the value of T3 as some 41 degrees Celsius. You have to convert it into Kelvin. Okay, always substitute in Kelvin only in this type of equation. So you will get the value of T4 as P3 is not P4 not, because P3 is equal to P2, P4 equal to P1 only. You will get T4 as 196 Kelvin. Okay, 196 Kelvin. Now what do you have to do? Cp the Q will be equal to Q refrigeration is equal to Cp into T1 minus T4. So Cp of air, actually this is a Bell-Coleman cycle. Bell-Coleman cycle, the fluid will be air only. So air refrigeration system, right? Air cycle. So Cp will be 1.005 kilojoule per kilogram Kelvin. So you have to always remember this value. This value won't be given in your problem because uh, these values should be in your memory always. Okay. So Q refrigeration is equal to Cp 1.005 into some T1. That's the value of T1. What's the value of T1? T1 is 273 plus 80. 283, 291 minus T4 196. So you will get a value around 95, some 95.4 kilojoule per kilogram. Should be. So students, I have calculated this value of Q in unit per unit kilogram. Per unit kilogram. So all these calculations were done on the basis that I am using a unit mass of air only. So I don't know the actual mass of air. So I am assuming the mass based on the assumption mass equal to 1 kilogram or 1 kilogram per second m dot. Since this is a flow is taking place, I am using the assumption of mass equal to 1 kilogram per second. So that is why I am getting this in kilojoule per kilogram. Okay. So this is the refrigeration amount, kilojoule per kilogram. or per unit kilogram. So how to find W? So W is nothing but Q refrigeration by COP. So COP have already found, right? We have already found. So 95.4 by 1.6, some 1.67, right? So you will get some value. What will be the value of work? You will get around 57 or something, right? 57. 57 kilojoule per kilogram. So make sure that your values are accurate. I'm just rounding up the values on some way calculation. Okay. So you got a W for unit kilogram of mass. It is 57 kilojoule per kilogram. So students, how to find the mass? How to so COP is done. Uh, Now we have to find second. First one was COP, and the second one was quantity of air circulated. Air circulated. How to find quantity of air circulated? This can be calculated since our calculations were all done based on one unit of mass per second. But actual refrigeration capacity as how much? 6 tons. This is very important. 6 tons. 6 ton. Very important. So what does that mean? Total amount of heat that can be extracted in this particular refrigerator is 6 tons. So this 6 tons should be calculated as converted into our standard kilowatts. How to convert it into kilowatts? I have already taught you. So 1 ton equal to some 3.5 kilowatts or 3.5 kilojoule per second. So 6 ton is 3.5 into 6. How much? 6 3.5 into 6 will be around uh, wait 21 kilojoule per second. Okay. So refrigeration effect RE will be 21 kilojoule per second. But for one unit of mass, it was around 95 95 kilojoule per kilogram, right? So the mass per second will be mass flowing, the quantity of air circulated per second, and that will be total 21 by 95. 21 kilojoule per second by 94 kilojoule per kilogram. So this will become a value of around 0.22 kilogram. This kilojoule cancel. This kilogram goes upward. Kilogram per second. So in 1 second, 0.22 kilogram of air should circulate in that refrigerator in order to get 6 tons of refrigeration of 21 kilojoule per second of refrigeration. So what does it mean? In one second, 0.22 kilogram of air should circulate to get 6 ton of refrigeration. 6 ton of refrigeration. So that is how. So you have to have to find this mass to get mass per m dot. We have to total tonnage, total ton by refrigeration, Q refrigeration effect or the CPT4 T4, sorry, T1 minus T4. So this is how we calculate our capacity. Total done 6 done by Cp T1 minus T4, you will get m dot. Okay, so that is done. Now, actually, we are asked to calculate m dot in kilojoule per kilogram per minute. Okay, kilogram per minute. If we have to calculate 2 kilogram per second means 0.22 into 60 kilogram per minute. If you multiply it with 60, you will get in minutes. That value will be some 13.2 kilogram per minute. In 1 minute, you have to circulate 13.2 kilogram of air, so that 6 ton of refrigeration will be done. Okay. Now the for third one is we are asked to find the piston displacement. Piston displacement. So how in compressor and expander. How to find that? Actually, our system is like this. 1, 2, 3, 4. So this is compressor. So this one is compressor. This one is expander. So piston displacement of compressor and expander means how much amount of volume should be compressed. So how much volume should be compressed? The volume corresponding to V1. V1 amount of volume should be compressed to V2. So if you find V1, it means the piston displacement will be something around V1. Okay. So here expander, it will be V3. So we have to find V1 equal to is to be found out. V3 is also to be found out. So how to find V1? Since we are using air as working fluid, we can apply perfect gas equation. So P1 V1 equal to M dot R T1. So R will be some 0.287 for air, kilojoule per kilogram. Okay. So V1 is MR T1 by P1. So P1 value you know, R 0.287, T1 you know, M dot equal to some how much 13.2. So M1, actually this is M1, but mass remains constant, so you can use M1 equal to M dot 2 equal to M dot 3 equal to M dot 4. Any point mass will be same. So T1 known, R known, P1 known, M known, everything is known. So you will get V1 as, so you should be consistent with your units, okay? 38 centimeter, sorry, not 38 centimeter. So you will get a value around 11 meter cube per minute. Since mass is in kilogram per minute, so your unit of volume will be 11 meter cube per minute. It means piston displacement should be in 1 minute 11 meter cube of mass volume should be compressed. Okay, so that is the idea. That's the idea between piston displacement. 11 meter cube of air will be the available at position state 1 to be in 1 minute, which is available for combustion. Similarly, V3 is nothing but m dot 3 or m dot itself, R T3 by P3. So P3 T3 R m dot everything knows. M dot is 13.2 itself. So you will get V3 as value of V3 will be around some, sorry, actually we have to calculate V4, right? Piston displacement. So V4 is the higher, the Actually, we have to calculate V4 since 3 to 4. It's PV diagram. So this is higher volume. So this much amount of piston displacement should be there. Higher volume is the that is to be calculated. So V4 is m dot r T4 by P4. Everything is known. So you will get around 7.42 meter cube per minute. So these are the piston displacement of compressor and expander. Okay. Now last one we have to calculate bore dia. Bore dia in case of compressor. How to calculate bore dia in case of compressor? Actually V1 is not some much 11 meter cube per minute. Okay, but volume of a piston cylinder, a cylinder can be calculated. How? You might have calculated in case of engines and all, right? In thermodynamics or thermal engineering. So volume is nothing but how area, area, bore area, bore area into stroke length. Stroke length into speed will give you piston displacement v dot or so if it is double acting you have to multiply it with 2. So v1 will be obtained if 2, since it is given double acting, 2 into bore dia d1 square into pi by 4 will give you bore area into stroke length L. So L into N. N is given. L equal to some 200. How much was the stroke length? 200? 200 mm. N equal to some 240 rpm. Okay. So this is the equation. So V1 is known. L and N are known. So you can calculate D1. So D1 will be uh, D1 38 centimeter. 38 centimeter. So check here. You have to be you have to use the same as SI unit itself. Then after calculating, after getting the final value, you can convert it into any type of unit. Okay. While calculation, you should be consistent with units. Okay. So I'm not showing you the calculation down. I feel you are grown up enough to calculate by yourself. So similarly, D4 can also be calculated for expander. You will get 31.3 centimeter. So these are the bore dia of compressor and bore dia of compressor and expander. Now fifth one, power, total power. But W is calculated as how much? 57 kilojoule per kilogram. But total power will be what? W into m dot. W into m dot will give you total power. So since this is for 1 unit of mass, we have some 0.22 unit of mass, then total power will be W into m dot. So W into or 57 into 0.22, actually 57 kilojoule per kilogram into 0.22 kilogram per second will give you 57.22 will be some value around how much? Okay, you 57 into 0.22 kilojoule per second. So kilojoule per second is kilowatts. So you calculate this value. Okay. So this will be the total power. So this is how we solve solve the problems based on Carnot cycle and Bell-Coleman cycle. I will give you some more one more problem as an assignment to try to solve it. If you are facing any difficulties, feel free to contact me. Okay. So in the next session, we will move to the aircraft refrigeration. There are different types of aircraft refrigeration. So that is an open cycle. So as of now, we have discussed only closed cycle because the air is being recirculated in the refrigerator without getting leaked into the open space. Okay, so this is a closed cycle. In aircraft refrigeration, it is an open cycle. So don't worry, I will try to make it as simple as possible. So as of now, I will stop this session. Thank you.